1 second is a small interval. We can barely grasp it before it is gone. The term 10 to the minus 2 seconds splits that brief measure into 100 parts. A stopwatch for racing uses hundredths of a second. A nanosecond, 10 to the minus 9 second, cuts a second into a billion parts.
A billionth of a second. To us it's instantaneous, but we still must divide it more finely. Cutting a nanosecond by another billion, we get 10 to the minus 18 seconds. Still a long way to go to reach 10 to the minus 43. But we're already dividing a single second into more divisions than there are numbers of seconds since the universe began. We must multiply that number by 1 trillion to reach 10 to the minus 30, and again by 10 trillion to reach 10 to the minus 43.
So, as you can see, 10 to the minus 43 seconds is a very short time.
The dual-force cosmos didn't last long. By 10 to the minus 35 seconds, the universe had expanded and cooled enough to cause another breakup in the primary forces. The short-lived unified force split again, triggering a wild expansion of our then tiny universe. Quicker than the speed of light, it grew from a size smaller than an atom to the size of a softball. This faster-than-light growth of the universe was possible because space itself was stretching, not because things were moving through space at impossible speeds. It was only after this inflation that some sort of matter appeared that we can create in a lab. Tiny building blocks of matter far smaller than atoms called quarks. At 1 trillionth of a second, one of the three forces of the universe broke up yet again, creating the more familiar four forces of present-day physics: gravity, electromagnetism, the strong nuclear force, which holds atoms together, and the weak nuclear force, which causes radioactive elements to decay. At this stage, the universe was nearly 2 miles across, and the temperature had cooled down to only about 1 trillion degrees. At a second old, the universe was still less than 200,000 miles across. It would have fit easily between the Earth and the Moon. The average temperature had dropped to 100 million degrees, still hotter than the inside of an average star. 1 minute after the beginning, if we use our solar system for scale, the whole universe, centered at the Sun, would reach 1/3 the distance to the first planet, Mercury. It took 100,000 years for the universe to grow large enough and therefore cool enough for atoms to appear. By then, the reign of energy came to a close, leaving matter to dominate the universe. Atoms appeared in two simple forms. Hydrogen atoms made up 90% of the matter that precipitated out of the energy. Helium, the next simplest, made up the rest. These two gases filled every cubic foot of the cosmos from one side to the other. Finally, the universe began taking on the mind-boggling proportions we've come to associate with it. Quickly, it reached a size that would envelop our entire galaxy. Virtually all the matter in the present-day universe had been created. The average temperature of space dropped down past 3,000 degrees. During its early phase, the explosion of the universe had been a dark affair, because light did not exist. But the creation of atoms liberated large amounts of light energy, called photons. This meant that the universe, which had been hot and dark, suddenly shined. Huge quantities of blinding white light filled every corner. Any features emerging in the still young universe would have been invisible because everything glowed with the same brilliant heat. But the time of light passed too, and space took on the blackness that we're familiar with today. It was an immensely colder cosmos than it had been. One force had given way to four. Matter dominated the universe, and slowly, matter began to reform and change. In this still young universe full of new atoms, two forces began to shape and mold the hydrogen and helium that was present. COBE, the Cosmic Background Explorer, is one of the great satellite observatories. It has detected in the deepest part of space slightly greater densities of gas, places where gravity could begin shaping galaxies.
In all probability, galaxies formed before stars, that there were huge concentrations of material resulting from what COBE saw in their recent observations, the fluctuations in the density of material that came out of the Big Bang itself formed little islands in the sea of radiation and matter that originated from the Big Bang. And these islands of material gradually condensed into galaxies, which were huge clouds, and within those clouds, stars formed from smaller parts of the clouds. So what we call a galaxy is a collection of stars and probably formed more or less as a unit.
In the regions where galaxies form, gravity and electromagnetic forces caused masses of gas to accumulate. Spheres of gas emerged. The atoms within them, crushed by gravity, grew hot. The densest parts reached temperatures of 15 million degrees. The universe witnessed the birth of its first stars. We'll return to the Practical Guide to the Universe on the Learning Channel.
There are many cars built safe enough, luxurious enough, and powerful enough to let you drive to the ends of the earth.
Shipping and handling to Piano by Candlelight, P.O. Box 11066, Department E, Chicago, Illinois 60611.
We now return to the Practical Guide to the Universe on the Learning Channel.
Today, billions of years later, creatures evolved from the matter created in the early universe, look outward from their small satellite orbiting a rather insignificant sun, and ponder the meaning of it all. The universe continues its expansion, and the remnants of the Big Bang glow faintly in the celestial background, awaiting mankind's analysis.
With ever more sophisticated observatories like the Cosmic Background Explorer, we're getting closer to discovering the true beginnings of the universe. But what can we say about its end? Will the universal expansion set in motion by the Big Bang continue forever? Or will all things fall back together in what's called the Big Crunch?
You know, there is an idea that the universe is slowing down. And then instead of one of these types of expansion, which is just in one direction, where you start with a Big Bang and it goes, that the self-gravitation of all these objects slows it down. So it does an accordion on you. It slows down and stops and then comes back together. And may go through several of these stages. Of course, when it comes back in, then you have the great collapse. And of course, all life as we know it and objects and mass is reconverted into elementary particles. And then the whole cycle starts over again. So it's a pulsating universe instead of just an expanding universe.
We're uncertain about the end of the universe because we really don't know how much total matter there is in the cosmos. If we count just the stars, we know there's not enough matter to cause it to collapse. If that's true, the universe will go on expanding forever. But stars aren't the only matter in the universe. Planets, moons, comets, asteroids, and dust count too. Optical telescopes don't show these well. With infrared telescopes placed in orbit, we're able to see even these kinds of matter. But there's still not enough to stop the expansion.
In astronomy, currently, there is a search for an elusive substance called dark matter. This is an unknown material, or possibly numerous black holes that might be present throughout the universe. This dark matter is called dark because it emits no light, which makes it invisible in space.
The Big Bang theory currently believed to be most accurate predicts the existence of dark matter, and the behavior of some galaxies also indicates its presence. These galaxies spin so rapidly they should fly apart, but they're held together by a huge gravity field, which tells us that there's more matter in these galaxies than meets the eye. Dark matter? Possibly. If there's enough dark matter in the universe to slow and then halt expansion, then all the galaxies in the universe will someday begin to drift back towards each other. They'll eventually crash and compress back down to that single point of pure energy, perhaps to begin the cycle all over again. But if the universe continues to expand, it's still doomed to destruction. Over billions of years, all the hydrogen used by stars to produce their bright light, will burn off. One by one, the stars in the sky will disappear, leaving a cold, lifeless universe behind.
For us humans, the question of whether the universe will continue to expand or finally contract is of no immediate consequence. In either case, it'll be billions of years before the end comes, and by then even our sun will be long dead. So for us as individuals, it will matter little, but will the race survive? Can humans evolve and become so smart that we can outwit the end of the universe? Another question to ponder. Perhaps from the small beginnings of the universe, the greatest force has emerged just in the last 50,000 years. It is the force of the human mind and imagination.